Thank you. So I'd like to thank all of the organizers for invitation and also giving me a chance to talk. So today I'm going to talk about joint work with Nadir Masmoudi. It's about kind of limit from some equation to the nonlinear Schrödinger equation. And the original equation is motivated by the water wave, but it's not exactly the true equation, but we consider some model equation. So this is the plan of my talk. I'm going to talk. So what we do is not so sophisticated, but somehow the formulation is complicated. So I need to give you some motivation, our motivation, and what we are going to do. And then afterward, I can tell you exactly what is our equation. Then before going to our results, I briefly mention some related works, and then give you our result. Then I can briefly explain, I hope I can explain some ideas, some simple ideas in the proof. Okay, so let me start with our motivation. So the nonlinear Schrödinger equation is well known as a sort of universal approximation, in particular in 1D, for many different nonlinear wave equations, which are much more complicated than the nonlinear Schrödinger equation, to describe some specific behavior that is global, not really global, but long time dynamics of a special sort of solution, which is concentrating in the Fourier space. In other words, it is very close to a single frequency or a monochromatic wave. And then if the equation is governed mainly by the linear dispersion and the nonlinear resonance, then for quite a general equation, nonlinear wave equations, we can at least heuristically derive the nonlinear Schrödinger equation. It's a bit vague, but somehow this characterization is enough to tell you our motivation. So what we want to do is somehow to extend this well-known theory to derive the nonlinear Schrödinger equation to more general solutions and to get more different dynamics by considering not only one frequency, but many frequencies. And if we consider many frequencies, then we can expect to have more resonance, nonlinear resonance between different frequencies. That's why we can expect to have more variety of dynamics. So this is our, roughly speaking, this is our goal. But before going to this direction, let me briefly recall how we can derive the nonlinear Schrödinger equation in the case of almost a single frequency. This is just a heuristic and well-known argument. And so for this for the heuristic derivation, you can just consider some abstract form of nonlinear wave equation, the second time derivative with and some spatial derivative operator with nonlinear term. So in this talk, I will denote the Fourier multiplier by underline. And for the moment, the form of omega, the Fourier multiplier, doesn't matter so much. But of course, we need dispersion. Dispersion means that the second derivative of omega is not 0. Then nonlinear Schrödinger equation can be derived by putting some ansatz for this solution in the following form. So we rescale space and time and also the amplitude by some specific order. And here we put the plane wave solution to the linear equation. So this is simply the plane wave solution for the linear part. And this part is slowly varying because we put small parameter epsilon here. And so this means that, of course, the plane wave is a solution to the linear part and not a solution to the nonlinear equation. But in this way, we can somehow get the solution to this nonlinear equation as a perturbation from the plane wave solution to the free equation. here, the scaling is chosen such that space and time is scaled by in a parabolic way. That's how we get the Schrödinger equation. And also here, I'm removing the group velocity from the solution. So you will see in a minute why we need to remove this factor. But anyway, by injecting this form, you can get at least formally an equation for this new variable, capital U, which looks like nonlinear Schrödinger equation. And so this scaling in particular means that the capital U in the Fourier space is concentrating or, by order epsilon. Okay. So I don't repeat the precise computation to derive the nonlinear Schrödinger equation, but rather I will heuristically explain how we obtain the linear part and the nonlinear part of the nonlinear Schrödinger equation. So first, for the linear part of the Schrödinger equation, it is simply coming from the second order expansion of the Taylor, second order Taylor expansion of omega. And because we assume that the solution in the Fourier space is concentrating by order epsilon, we can naturally expand the phase factor omega into order epsilon. So the first factor is, of course, independent of C. This means in the phase part, this gives us just the oscillation, which is uniform in space. So this factor will give us time oscillation. And the second factor is linear in C. So this means in the phase factor translation in space. So this is the first order term. Then if we remove these two rather trivial factors, the next factor is C square. And C square is simply Laplacian. That's how we get the nonlinear Schrödinger equation, because this is just Laplacian. And since so the scaling here is to make this second order term to be of order 1. Therefore, the 0th order term becomes of order 1 over epsilon square, and the first order term becomes 1 over epsilon. So we need to remove them. Therefore, here, in the rescaled variable, we need to remove this factor from here. It is 1 over epsilon square. And we also remove the group velocity, which is of order 1 over epsilon. Then we get the Laplacian of order 1. So that's the linear part. Then the nonlinear part, to understand the nonlinear part, we need to think of the nonlinear resonance. So the nonlinear resonance in our setting, or in most of the nonlinear dispersive equations, is simply the following. So you consider, for the quadratic nonlinearity, you consider the product of two plane wave solutions for the free equation. And if the product becomes almost like another plane wave, that is, if the sum of the phase is equal to the phase of the sum, then we say these two plane waves are resonant. And of course, this need not be exact equality, because we consider approximation. What matters is approximate equality here. And here we consider second order expansion of omega. So what matters is also Taylor expansion of this equation and the 0th order and the first order. Then first 0th order cancellation, or 0th order expansion of this equation, is simply the exact equality here. And we call this time resonance. And because that is because time resonance means product of two plane wave, that time oscillation is somehow cancelled. Then the cancellation in the first order of this of the Taylor expansion of this equation is simply in this form. So the derivative of omega is the same at P and Q, which is called the space resonance, because this means that two plane waves are propagating in the same speed. So we can also consider the higher order vanishing of this equation, but the higher order doesn't matter for the NLS approximation. So only these two resonances are important. And the importance of resonance is that if we don't have such relations, then product of two waves are somehow oscillatory compared with linear evolution. Therefore, for the long time dynamics, it has little impact because the oscillatory integrals gives us some cancellation. Then we can observe why this cubic term appears in the limit, because somehow this cubic term is the simplest form such that we have resonance in a trivial way. Because if you consider the polar coordinate for this function, I mean for the output, then this cubic term oscillates exactly as the solution itself. So this implies it is resonant in any sense. Therefore, this is quite very much resonant. And this cubic term is the simplest form of this character. That's how why we get this nonlinear term in this derivation. So all of this is about almost single frequency case, but this time resonance and space resonance will be also important in our analysis. Okay, so let me go back to our question. So we want to extend the previous argument to more general solutions. More precisely, we want to have more frequencies, and we expect that more frequency would lead to more non-trivial resonance. Here, non-trivial means resonance which is different from the cubic nonlinear Schrödinger equation. So to be more precise, now I want to fix our equation. Of course, we can consider, for this purpose, we can consider just a mathematical model, but fortunately, there is an interesting equation from the physics, which is from the water wave. So if we consider, now I talk about the water wave equation, but skipping all the physical background. Anyway, we consider, if you consider the water wave in 2 dimensions with infinite length, with finite depth, and then after some reduction, it is known that the equation takes this form. So here, by the way, I consider the water wave equation with gravity and the surface tension and the finite depth. Then at least the dispersive relation is well known. For example, you can find this complicated formula from Wikipedia. And it is written by using a single physical constant, which is called the bond number. And it looks a bit complicated, but somehow exact, I mean precise, explicit. And then this part is just a linearization of the true equation. And there is much more complicated nonlinear term, and it is in particular quasi-linear. And most of the complication of the water wave equation is coming from this part, but somehow we are ignoring that feature. And then we just replace this complicated part by a simple model, which is not so wild, I mean singular, and quadratic. So as I said, this part is quasi-linear, and therefore we have to lose if we use simple perturbation argument, some derivative. But here we are assuming that this lambda, also Fourier multiplier, is not so wild. In other words, it is dominated by omega. So this means we can treat the nonlinear part as just a perturbation from the linear equation. In this way, we can avoid all the issues coming from the derivative loss from the nonlinearity. And it is, heuristically speaking, it's not a big loss for our purpose. Because in any way, anyway, we consider solutions which are concentrating in the physical space, Fourier space. That means it's getting like almost like analytic in X. Therefore, the solution is very smooth. So the regularity issue shouldn't be a big issue. Of course, to treat it is really non-trivial. But now we ignore that issue. Okay, then but we want to use this omega, so we choose this omega on purpose. That's because, not because of this exact form with the tangent hyperbolic, but what we care for is the concave and convex structure of this omega. So the special property of feature of this omega is the following. If you draw the graph of omega prime, then it is like this. So up to some frequency, the omega prime is decreasing, and after that frequency beta, it's increasing. This means for low frequency, omega is concave, and for high frequency, it is convex. And this structure gives us a lot of non-trivial resonance. For example, you can observe that between this omega prime and this value, there are two frequencies, exactly two frequencies at which omega prime is the same. So this means this frequency and this frequency propagate in the same speed. Therefore, you have resonance between them. This kind of thing cannot happen if omega is everywhere concave or everywhere convex. And indeed, as long as we are in 1D, you can easily observe that if omega is everywhere convex or everywhere concave, there is no resonance, except for this cubic nonlinear Schrödinger. So we need this structure to have something interesting. And somehow this is the minimal requirement to have this structure. And so indeed, for the water wave equation, we assume that the three physical factors, the gravity, finite depth, and the surface tension. If one of them is absent, then you can observe that omega is either convex or concave. So we need all of these physical factors, I mean, to get our result interesting. So now I want to set up our equation with a slightly more simplification. We had two second-order equations, but now I want to make it to the first order just for the sake of simplicity. So the first-order version of equation would look like this. So now it is like just first-order time derivative and first-order space derivative equals some quadratic term. So omega is the square root of the previous expression, and it is like c for small frequency and c to the power 2/3 for large frequency. So by going from second-order equation to this first-order equation, I'm neglecting some factor. That is, in the second-order equation, there are left-going waves and right-going waves. But in this form, we are taking only left-going waves. So we are neglecting the interaction between left-going and right-going waves. But it gives just a little difference in the result. So just for simplicity, I'm neglecting the right-going wave. We can actually treat the second-order equation, but the notation becomes more complicated. So just for simplicity. Now, this equation is roughly speaking, for example, if you consider low frequency, then I omega underline is just like dx. And also, I nu bar underline is like dx. So this is a very simple wave equation. But of course, the dispersion is important for our analysis. Okay, so let me be more precise about the property of this omega, or the property we need to get the interesting result. So as I said, there is some special frequency beta at which omega changes from concave to convex. And also, the group velocity goes to infinity in high frequency. Actually, these two properties are essentially what we need for omega. Then we can prove the following four properties. First, there is a unique frequency at which the group velocity is the same as that of group frequency 0. So this frequency causes very strong resonance, and it is well known in the water wave equation, and it is called long wave, short wave resonance. There is another also special frequency, which I denote by alpha, where the twice of omega equals to omega of the twice alpha. And it is called the second harmonic resonance. It also causes some strong resonance. But besides these special frequencies, we can also find some weaker resonance for general frequency between 0 and this special frequency gamma. Indeed, for each frequency in this interval, we can find a unique frequency such that these two frequencies generates the time resonance. So time resonance means this equality. And indeed, this special pair of each frequency exhausts all the solution for this equation. Besides the trivial one, which is when one of them is 0. And also, for each p, we can find a unique pair, p star, such that the space resonance occurs. So, and it is also the only solution besides the trivial case when p equals q. And these properties follow from the first two properties. But in our case, we can also prove that these two cases, namely the time resonance and the space resonance between 0 and gamma, do not coincide. So P1 and P star are always different. Okay, so this list is what we actually need for omega. Then, before going to our result, I briefly mention only a few of related works. So, of course, nonlinear Schrödinger limit is very well known, and there are some mathematical rigorous study. And actually, our study setting is somehow motivated by the works by Schneider and his collaborators. So they considered a case with when solution is concentrated at a single frequency, but they can consider many different models. And in particular, in some cases, they can also prove the failure of the NLS approximation when there is some resonance, even for a single frequency. And for the water wave model equation, that is what I showed previously. Without the surface tension, they also prove the convergence to the nonlinear Schrödinger equation in the single frequency case. And for the full equation, there is also a work by Tots and Wu in the case when the depth is infinity and the surface tension is 0. But in all of these works, the remainder is estimated in the original space, and because the amplitude of the main term is epsilon, the remainder has to be smaller, and it is of order 3/2. And I will show in the next slide, in our setting, we estimate the remainder in a different way. We actually estimate the remainder in the rescaled variable. So in that sense, the setting is somehow a bit different. But anyway, for the single frequency, it is more or less understood because we don't have so much resonance. On the other hand, for the water wave equation, there is also there are many recent works about the global existence of general solutions. And so in the same case as here, when the depth is infinity and the no surface tension, then there are at least 3 groups prove the global existence for small data. Araza and Dero, Ionescu and Pusateri and Ibrahim and Tataru. And also in the case with the surface tension, they prove the global existence. So this is some, at least in the technical part, these works are quite much related to us because in their case also the non-resonance plays a very essential role. However, the setting is somehow disjoint because their initial data are small. Actually, our initial data is also small. However, their data is localized both in X and Xi. On the other hand, our data is localized very much in Xi, but that means we cannot make it localized in X. Therefore, data is somehow quite different. Anyway, the technique, there is some similarity in the technique. And also for the water wave, there are other regime of the limit, and in particular, there are many works about the KDB scaling. And in this case, actually, the limit rigorous proof of the limit is better. And Schneider and Wayne proved essentially all case of kappa. This is the bond number, including the singular case when kappa is 1/3, where the third order derivative vanishes, and you get the fifth order Kawahara equation. So somehow KDB scaling has been settled. Even with these three factors, gravity, depth, and surface tension. And heuristically speaking, KDB case is slightly easier because you don't have to consider or investigate the nonlinear resonance. So, of course, there are many more other works, but I cannot really mention all of them. Now, I go to our result. So, we first rescale and reformulate our equation, and the convergence will be given in the rescaled variable. So we start with this model equation for the water wave, and first we rescale the unknown variable by this parabolic scaling. Then we want to consider a solution which is not necessarily concentrating at single frequency. And this requires us to treat all frequencies somehow equally. And for that purpose, we decompose this rescaled solution in the frequency. So this is a decomposition into unit intervals in the C variable by smooth cutoff. Then I denote each component at frequency k by uk. So this frequency k corresponds to epsilon k in the original frequency. So this decomposition is actually this composition in the Fourier space of order epsilon in the original variable. Then we need to remove the time oscillation and the space translation. So after removing these two factors, I denote the unknown variable by WK. So because these two factors are divergent as epsilon goes to 0. And this is, as I said before, given by just the Taylor expansion of omega. And the next term is denoted by R, K, and it is like a Laplacian, but the coefficient depends on this frequency K. Now, the equation for the original equation can be rewritten for this new unknown variable, WK. And the equation for this guy is complicated, but it is equivalent to this equation. And we consider the equation for this guy and the convergence for this guy. So precisely, the equation looks like this for WK. It's complicated, but on the left-hand side is just like Schrödinger equation. And the right-hand side is like a quadratic term, which is divergent by the order 1 over epsilon. And it has oscillation in time in general. Also, it has space translation. And if it is time non-resonant, then this is oscillatory. And if it is space non-resonant, then they are propagating in different coordinates. So therefore, we can expect that we can somehow compensate this divergent factor. So anyway, omega is given by the difference for the time resonance equation, and C and C1 and C2 are just group velocity, the difference of group velocity. Then, yeah, as I said, time resonance means that this factor is almost 0. And the space resonance means the velocity are almost the same. So if omega is non-zero, then we can integrate on this very rapidly oscillating factor which gives us epsilon gain. Therefore, we can compensate this factor. And also, if the velocities are different, namely if it is space non-resonant, then we can observe that they can be at the same place only for short time. Exactly, they can meet only for the time interval of order epsilon. But of course, it is only if these guys are spatially localized. So in order to use this factor, we need to assume somehow these components are localized in space. And the minimal requirement for that seems the following. So we assume that it is in L1 in space. And the time dependence here assumes that somehow uniform in space. And for that purpose, we use this space-time norm, where we take the supremum first in time, and then we take the L1 norm in space. So this means if this is finite, or if this is small, then the solution may be changing in time, but its space position is not changing so much. If it's moving, then this norm will be huge. But so this norm is very good to use the space non-resonance. However, we cannot put our all components into this norm because there are some components which are moving in space. For that part, we use a slightly weaker, not really weaker, but a different norm, which is defined by this. So some component is bounded in L1, but may be moving in space. However, it is small in L infinity. It is of order 1, of order epsilon. So our function space is the sum of these two spaces. So roughly speaking, the component Wk consists of the following 3 types of waves. The first one is the main part is like this, which is not moving in space. And this will be the main part for the nonlinear Schrödinger equation. But there are also other components which is moving very fast in space of order by the speed of order 1 over epsilon. And also by integration in time of this kind of factor, we get some wave which is spreading in space, like this pink wave. And that's why we need to use not only this L1, L infinity, but also this space y. For example, for this case, it is of order 1 in L1, but is of order epsilon for L infinity for this component. That's why we need to introduce this space y. Then the original solution, or the rescaled solution U, is a kind of superposition of this kind of waves. So somehow it's we regard it as a superposition of wave packets. However, this is only for the main part, and we have also these other parts. Okay. Now, so as I said, there are some special frequency which I denoted by alpha or gamma. Gamma is the long wave, short wave resonance, and alpha is the second harmonic resonance. We cannot really treat them equally as the other frequency. So we need to penalize them by putting some weight here. So 1 over rho is the penalty for approaching these special frequencies. Then besides them, we can treat all frequencies equally. And the first result is about existence of a solution which is uniform in epsilon after the rescaling. So before the rescaling, this means existence to the time of order 1 over epsilon square. So, and we don't assume that the solution is concentrating at any frequency. We can consider any initial data which is, however, bounded in the summation in the L1 space with this penalty for the special frequency. And we also need to assume that it is small. But then we can prove that the solution W for all for each epsilon small enough exists on time interval which is independent of epsilon, and it is also bounded by this small factor. So actually, in the case of single frequency, you don't really need the smallness of the initial data. However, here we need to assume that the initial data is small. That is because we have time-resonant interaction, which is time-resonant but space non-resonant. As I denoted, there are a general frequency pair between 0 and gamma. And this time-resonant and space non-resonant interaction taking place in the time interval order epsilon. So if you shrink your time interval, then this kind of interaction is still there. You cannot make this interaction smaller by shrinking your time interval. So smallness of time interval t does not help at all for this type of interactions. That's why we need to assume the smallness of the initial data. Okay, so this is the first result. It's about the uniform existence. Then the second is about the convergence as epsilon goes to 0. But for convergence, the previous setting is somehow too general because we treat all frequencies equally. But to get some limit, we need to assume more. So now we assume that the solution is somehow concentrating not to one frequency, but to some prescribed finite number of frequencies. And the prescribed finite number of frequency is denoted by P. And with some condition, this is to ensure that whenever we have a time resonance, then the outcome is also treated as the special selected frequency. Then we consider special initial data in that form. We assume that the solution is concentrating at these frequencies with some fixed form. Actually, we can put some remainder here, but for simplicity, I'm omitting that. And we assume that this is bounded in our space and small. Then we can derive a kind of nonlinear Schrödinger limit for each component. So the solution is also in this form. And now the function here, AP, will be solution of some nonlinear Schrödinger equation or some modification of that. And the remainder is somehow small. More precisely, this part is going to 0. We need to allow some part is only bounded in the space y. However, space y means it is of order epsilon in L infinity. So this does not go to 0 in L1, but it goes to 0 in any LP, p bigger than 1. So somehow the remainder is going to 0, and the main part is a solution to the following system of equation, which is also a bit complicated. So first, the main equation for the limit profile is the nonlinear Schrödinger equation. However, it is now coupled because we have this space resonance pair. For each p between 0 and gamma, we have another unique frequency at which the group velocity is the same. And these two components are coupled in the limit nonlinear Schrödinger equation. And the coefficient may be defocusing or focusing. Actually, we can easily observe that the Hamiltonian for this coupled NLS has a sign indefinite energy part because our omega is concave and convex. And AP, one of AP is coming from the concave part, and the other is coming from the convex part. This means the energy part has different sign. Therefore, the Hamiltonian for this coupled equation is sign indefinite. Anyway, this is the main equation. However, at the special frequency gamma, we get another equation, which is not exactly the Schrödinger equation, but it contains sort of derivative and integral in time. And this equation is actually known, and it's often called the Benny equation. Actually, there are many equations which are called Benny equations, but it is one of them. And there are some mathematical studies. Please note here, A gamma and A0 is not really the same as other AP. So in the previous slide, sorry, I didn't mention this. I put this weight outside of A. This means AP at P equal gamma contribute only by order epsilon to the 1/2, and AP at p equals 0 contribute by order only by epsilon. So actually, this equation is somehow describing smaller order dynamics. We assume that A gamma and the component at gamma and 0 are small of this order. And also at the second harmonic resonance frequency, we have another equation for which I don't know the name. I couldn't find this equation, but it also contains some integral nonlinearity. So somehow we get some modification of the nonlinear Schrödinger equation by space resonance. On the other hand, we have also time resonance. It gives us another modification by initial layer. So the initial data for the previous equation is not really the initial data we choose for the original equation, but it has to be changed by using the scattering operator for this type of transport equation, because we have a time resonant interaction which takes place in very short time, and it changes somehow the initial data. So for each pair which is time resonant, we need to consider this system of simple nonlinear transport equation. So this is just a transport and quadratic nonlinearity. And then at least for small data, we can get easily the scattering operator or the limit profile at time infinity. And the initial data for the previous equation is actually the final data for this equation. That's because the time resonance changes somehow the initial data. And we also need to take care of the same effect at frequency 0, which is now cubic in the nonlinearity. And also at alpha, it is slightly different, something like this. Okay, so it's a very long description, but anyway, this is the limit equation for our setting. Now, let me briefly mention some simple idea. It is actually not complicated. So the main idea is to use time non-resonance or space non-resonance or the weight function rho or the null structure, which is that the nonlinearity is vanishing at frequency 0. And I just explain how we use the time non-resonance and the space non-resonance. So the time non-resonance means that time oscillation factor omega is not 0 or of order 1. Therefore, we have this very rapidly oscillating factor in the nonlinearity like this. And roughly speaking, we can just integrate on this factor and differentiate the other factors. So integral of this gives us epsilon square. The differentiation of the other factor gives us 1 over epsilon. So in total, after this integration by parts, we get cubic term without any factor of epsilon. That's how we get cubic nonlinearity, and also it gives us some boundary term, but it is of order epsilon. So roughly speaking, in this setting, when it is completely time non-resonant, it's easy to estimate. And this is actually already in the single frequency case. But in other case, we need to use space non-resonance. And for space non-resonance, we use this norm, L1 in X and L infinity in T. But this estimate is also very simple. It is actually essentially the Fubini. So if you consider this type of interaction where two functions are traveling at different speed, then if you use this norm, then you can simply ignore the time dependence by first taking the supremum. And then after that, it is just Fubini, just changing the order of integration in X and time. Then we get a factor denominator coming from the difference of that velocity. So in our case, this is of order 1 over epsilon. Therefore, we get factor epsilon from here. I just want to mention that this argument doesn't seem to work in the classical weighted space in L2, because if we would use this type of space, then the gain would be simply just epsilon, square root of epsilon. That's easily observed by considering, for example, one of them is not traveling, but if the other is traveling at very fast speed, then of course the weight will penalize this guy, but the penalty will be just the same for the outcome. Therefore, from the weight, you cannot gain anything. And because we are estimating in L2 space, and the outcome in this form, the product of two different guys, will be spreading. And therefore, because the support will be of order 1 over epsilon, the gain in L2 space is actually epsilon to the 1/2. And therefore, for example, in this case, you can easily observe that the gain from this weight cannot be better than epsilon 1/2, as long as the weight is, for example, algebraic. And so the picture is simply like this. We have something which is not moving, and if the other guy is fastly moving, then the product will be somehow spreading. And therefore, this spreading and the support is of order 1 over epsilon, and L2 norm is 1 over epsilon squared. And therefore, we lose 1 over epsilon. So what happens in our case is that if we use this norm, then the penalty for this guy is very huge. And the penalty is 1 over epsilon. And therefore, even though we lose the factor epsilon from the support, so the outcome will be of order 1. Because this guy is very large in this norm, we gain of factor epsilon in this norm. Okay, so maybe I'm too early, but stop. Thank you.